In this video, we talk about Gaussian mean and principal curvatures, and we also discuss Gauss remarkable theorem. Let W be an Weingarten map of an oriented surface S at a point P on the surface S. The Gaussian curvature and the mean curvature of the surface S at the point P are defined by the Gaussian curvature is equal to determinant of Weingarten map, and the mean curvature is equal to half of trace of Weingarten map. Let gamma be the surface patch with first and second fundamental forms are given by equation 54 and 55. Let's define the symmetric matrices corresponding to these first and second fundamental maps. They are given by F1 and F2. It's given in equation 56, writing the first fundamental form and second fundamental form in a matrix form. Then the Weingarten map is with respect to basis sigma u and sigma v is given by the inverse of the f1 inverse and multiplied with the f2. This f1 inverse f2 is nothing but the Weingarten map at point P on the surface S. The Weingarten map, while defining a point let's take a point P on the surface S. So the Weingarten map has the eigenvalues and the eigenvectors. The eigenvectors form the tangent plane. They form a basis of the tangent plane, and the scalars kappa 1 and kappa 2, these are the eigenvalues of the Weingarten map. The eigenvalues of the Weingarten map are called as principal curvature of the surface S. The eigenvectors of the Weingarten map are called as principal vectors of the surfaces. If the eigenvalues kappa 1 and kappa 2 are equal, then that point is called as umbilic. The point on the surface at which the Weingarten map has the eigenvalues which are equal, then that point is called as umbilic. So the Weingarten map, the eigenvectors, they form an orthonormal basis of the tangent plane. The eigenvalues of the Weingarten map are called the principal curvature of the surface at that point, and the eigenvectors are the principal vectors. So we have a proposition that the Gaussian and the mean curvatures is determined through the determinant of the Weingarten map is nothing but the product of the eigenvalues, that is kappa 1 and kappa 2, that gives the Gaussian curvature. The trace of the Weingarten map gives the sum is equal to the sum of the eigenvalues of Weingarten map. So the mean curvature is given by the half of kappa 1 plus kappa 2. So we have a theorem corresponding to this. Let's say gamma be a curve on an oriented surface S. Kappa 1 and kappa 2 are the principal curvatures of the sigma with principal vectors at T1 and T2. Then the normal curvature is given by kappa 1 cos square theta, kappa 2 sin square theta. This theta is the angle between T and gamma dot. So the normal curvature is defined like this. What does it mean is that the principal curvatures at a point are the maximum and minimum values of the normal curvature of all the curves passing through that point, and the principal vectors are the tangent vectors of the curves giving maximum and minimum values. So the eigenvalues of and the eigenvectors of Weingarten map defines the principal curvatures and principal vectors at the particular point. So now we'll come to what is Gauss Theorema Egregium. So it's a Gauss remarkable theorem. What he has showed that, what he has shown that, let's take a surface which has the first fundamental form and second fundamental form, and define the Christoffel symbols as we have done earlier in earlier video. Then the Gaussian curvature of the surface patch can be it can be shown that the Gaussian curvature of a surface patch can be expressed through the first fundamental form, only first fundamental form. The theorem is the Gaussian curvature of a surface is preserved by local isometries. That means K, the kappa, the Gaussian curvature can be expressed only in terms of first fundamental form. We don't need any information of second fundamental form to find out the Gaussian curvature of a surface patch. That is the Gauss Theorema Egregium. Thank you.